The second property of water that we're going to talk about is moderation of temperature by bodies of water. Again, this is one of the three properties of water that has everything to do with the fact that water molecules form hydrogen bonds with each other. So first of all, water can absorb heat from warmer air, cooling down the air, or it can release any heat that has stored in it, any energy, to cooler air to warm that air up. When it does so, when it absorbs or releases this heat or this energy, it can do so in really large quantities without actually changing its own temperature very much. So if we're going to explore these two particular points, first of all, we need to understand what is heat exactly and what is temperature. But again, before we can do that, we have to take a couple steps back and take a second look at this idea of energy. We've introduced energy before, right? In chapter 2, we introduced energy for the first time, saying that it's the capacity to cause change. We understand there are different kinds of energy. We introduced potential energy, for example. This is the energy that matter has based on its location or its structure. We looked at potential energy for the first time when we were looking at atomic structure and electrons. And we talked about how electrons have this certain amount of potential energy associated with them. The other kind of energy that is highly prevalent in the world around us is kinetic energy, and this is the energy of motion. Now, you can't see it, but all matter, all molecules, all atoms are constantly moving. You can't see it, right? When you look at a table or a wall, you can't actually see the molecules, number one, and number two, you definitely cannot see them moving, but they have this vibration. They're all constantly vibrating, and it's a random vibration. There's no direction to it. But this type of kinetic energy, this random motion of atoms or molecules, is specifically called thermal energy. So when you measure the temperature of a body of matter, what you're doing is you're actually measuring the average kinetic energy of the molecules in that particular body of matter. And in science, again, we're using, the metric system, so we tend to use the Celsius scale for measurement of temperature. Let me give you an analogy for what temperature might be. So you all took a recent quiz, and the class average, right, the average grade on that quiz would be the same thing as taking the temperature of the class to see how well you guys did, right? So again, temperature is the average kinetic energy of molecules in that body of matter. Now, temperature, if we think about it, is definitely different from total thermal energy that a body of matter would have. So let's see. Let's imagine that we have, let's say we have a small cup, right? And this cup is filled with water. And then let's say I'm totally crazy and I go ahead and I bring in a kiddie pool into class. And I fill that kiddie pool also with water. Now, let's say I let those two sit in the classroom for a week. If I were to take a thermometer and stick it into either one of those two bodies of water, either into the cup of water or into the kiddie pool of water, the thermometer would read the same, right? Irregardless of the volume here, either the large volume in the pool or the small volume in the cup of water, both of those bodies of water would read the same temperature because they've had a chance to acclimate to the temperature in the room, right? So they might both read, let's say in our classroom, 69, that's definitely not Celsius, 69 degrees Fahrenheit in both of those cases. So temperature, average kinetic energy, is essentially not dependent on volume. On the other hand, if I asked you to think about total thermal energy of the water molecules in the cup versus total thermal energy of the water molecules in the pool of water, what do you think? Which one would have a higher total thermal energy? If you thought about this and you picked the kiddie pool, you're right. right? Because in order to calculate the total thermal energy, you'd have to take into consideration the energy of each one of those individual water molecules in those two respective bodies of water. Obviously, the kiddie pool has more water in it, so it would have more total thermal energy. Okay, so temperature does not depend on volume and is the average kinetic energy. Total thermal energy would be the addition of all the thermal energies of all the molecules of that particular body of matter. One more point that we have to cover on this slide, and that's heat, right? So in wintertime, right, I enjoy drinking tea, and I enjoy drinking my little mug of tea, which I happen to have right here, and I like to hold it. I like to hold it because I can feel the heat of the water molecules in my tea coming through the ceramic of my cup and into my hands. So heat is actually thermal energy in transfer from one body of matter to another. So I'm feeling that kinetic energy being transferred from the water molecules in my tea to the ceramic of my mug and then into my hands, and it's being transferred there to my cells, and I can then sense that energy transfer by feeling a hot cup of tea. Okay, one more point to bring up, and this is an idea of specific heat. So by definition, the specific heat of a substance is the amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree Celsius. All right, so how much of that energy is required to change the temperature of a certain amount of a substance? Now, for water has a really uniquely high specific heat. And this is all because of the fact that hydrogen bonds, in order to make them and break them, this requires energy. And because water can form so many hydrogen bonds, it requires a lot of that energy to be transferred in and out. So let's think about what happens when hydrogen bonds break in terms of heat and what happens when they form. So first of all, heat is absorbed when hydrogen bonds break, and then heat is released when hydrogen bonds form. Maybe to help you remember this. Okay, so I mentioned I like tea. In order to make my tea, I take my tea kettle, I fill it with water, and I put it on my stove. I have to turn my stove on. I have to supply that energy, supply that heat in order to warm up my water enough to make tea, and then also to cause steam to come out of my tea kettle so it'll whistle. Now, that steam is essentially water molecules that have broken all the bonds with any of the adjacent water molecules, broken those hydrogen bonds, and they've managed to escape that body of water inside of my tea kettle. So you need to add heat. Heat needs to be absorbed when those hydrogen bonds break so that the water molecules can escape as steam. On the other hand, when you take water and you freeze it down to ice, in solid ice, water molecules form their maximum of 4 hydrogen bonds with their neighbors. And that's what gives ice that beautiful crystal-like structure to it. So heat needs to be released, cool down the water to freeze it, so that those hydrogen bonds can form, so that you can actually form that solid ice structure. All right, so hopefully that makes sense. And now we can take all of these concepts and use them to talk about how is it exactly that water can help to regulate temperature, again, permitting life on our planet. So because, first of all, water has that high specific heat, it can minimize any temperature fluctuations to within limits that permit life. It can absorb a lot of heat or give up a lot of heat without really changing its own temperature very much. And so it helps to regulate temperature of air, for example, or a body of an organism. Let's take a look maybe at California as our first example. So here we're looking at the coast of California. We see the Pacific Ocean. Pacific Ocean in this example is at a 68 degrees Fahrenheit. So not super warm, but still moderately pleasant. If you take a look, this is on a particular day, if you take a look at all of the cities that are on the coast, so Santa Barbara, you've got Los Angeles, San Diego, they're all in, the mid 70s, low to mid 70s. Very pleasant along the coast. Same day, same sunshine. As you continue moving further away from that coastline, you can see that the temperatures start to climb into the 80s and 90s, and then 106, right, once you get further inland. Why does this happen? Well, when you're further inland, you're farther away from that body of water that is the Pacific Ocean. And the Pacific Ocean isn't there to absorb that heat during the day to cool the surrounding air down. And so this is why you have much more drastic fluctuations in temperature when you're further away from bodies of water. On the coastline, right, night and day, probably not huge fluctuations, because in the daytime, the water absorbs that heat from the air, cooling the air down. And then at nighttime, when the air turns cooler than the water, then the water releases that heat back into the air, warming it back up. Okay, so that's maybe in an ecosystem how water could help regulate temperature. But what about in an organism? Water can do exactly the same thing, right? So let's say we're sitting in the classroom in May and the air conditioning goes out. I've used this example before, right? What's going to happen to you is you start sweating. This is your body's way to respond to the environment to help regulate your homeostasis. What we didn't talk about is how exactly is it that sweat helps to cool you down. So the first thing we need to understand is what is evaporation. So evaporation is the transformation of a substance from liquid to gas. So when you sweat, your body puts out a layer of liquid, water, on the surface of your skin, and that sweat begins to evaporate. When the sweat evaporates, this is what cools you down. This is a process that's called evaporative cooling. This happens not only on the surface of your skin, but also on the surface of the ocean, helping it to regulate the temperature of the air around it. But how? Maybe it's not exactly clear how evaporative cooling works. So let me give you an example. Let's go back to taking temperature, right? Temperature is average kinetic energy. When the temperature is high, that body of matter and its molecules have a lot of kinetic energy. When temperature is low, they have less kinetic energy. So I use the analogy of your quiz grades, right, as the average being the temperature of the class. So let's say on that quiz, I said, okay, everybody that scored 100, you don't need to finish the rest of the class, you're doing great, you can go on to take A&P. And you just left, and you took your grades with you. When those high-scoring grades leave, what happens to the remaining class average? If you think about it, the remaining class average, the remaining class temperature, is going to decrease if those high grades leave the class. Same idea for temperature. As those molecules of water evaporate, the ones that are evaporating are the ones that have the greatest amount of kinetic energy because they can break bonds, those hydrogen bonds with all neighboring water molecules, and they escape. And they take that high kinetic energy with them. When they leave and they take that high kinetic energy with them, the remaining liquid or sweat in that body of matter or on the surface of your skin, it's going to cool down. The average temperature or the average kinetic energy, aka the temperature, is going to decrease on the surface of your skin or decrease in that body of matter. So that's how evaporative cooling works.